Good day everyone. So this is the first lecture in your respiratory module. So for physiology, the first lecture would be mechanics of ventilation. So today I'll be giving you the lecture on mechanics of ventilation. So these are the learning objectives of this lecture. By the end of the lecture, everyone should be able to list the functions of the respiratory system and list the functions of the upper and also the lower respiratory tract. And also you need to be very well versed in the mechanics of ventilation. And I'll be touching a bit on the pulmonary compliance, surfactant, and also work of breathing. So these are the functions of the respiratory system. So we can divide the functions into two big arms, which are the respiratory function per se. So this is the important functions and this will be the focus of our respiratory module. And also there will be some non-respiratory functions. So these are the other functions of the respiratory system which are not involved in the exchange of gases. So for the respiratory function, I think this is very common and I think everyone knows about this. So it is actually for the exchange of the gases. So of course we breathe in oxygen, so we need to supply oxygen to the cells in our body for cellular respiration, and also we need to take out the carbon dioxide which will be excreted out from the lung. Okay, so these are the respiratory functions. So this is the main bulk of function of the respiratory system. Then we have these non-respiratory functions. So again, we can divide it into defense mechanism. So in defense mechanism, of course, we have ciliary function. So if we look at the respiratory tract, especially the upper part of the respiratory tract, it is lined with cilia. So the cilia is actually serves as a defense mechanism. So the cilia will actually move out the any infection, so any dust, or any pathogen from the respiratory tract. And then there's also the presence of IgA, immunoglobulin, and also there's also macrophages. So these two things, IgA and also macrophages, would be in play, especially if there's any bacterial infection or any viral infection. And then we also have cough reflex. So even though this is a reflex, actually this is a protective mechanism. So let's say you have you eaten something and you choke on something, so there will be a cough reflex for you to cough out the things that you have choked off. Okay, so that is the function of cough reflex. So these are all under defense mechanism. And then respiratory system is also important to maintain the acid-base balance. Okay, so again, I think you will learn more about acid-base balance in urinary module. But here, the respiratory system would be able to flush out carbon dioxide. So carbon dioxide is actually acidic because it can dissociate into hydrogen ion and also bicarbonate hydrogen ion and also bicarbonate ion. Okay, so when there's a lot of carbon dioxide being excreted out, so we are actually excreted acid out. So that's how the lungs or the respiratory system helps in the maintenance of acid-base balance. Okay, next would be the I think all of you remember about angiotensin 1, angiotensin 2. So you have learned this in your BP regulation. So in long-term BP regulation, meaning in the renin-angiotensin-aldosterone system. So angiotensin 1 need to be converted into angiotensin 2 because you know angiotensin 2 is a potent vasoconstrictor and we also stimulate the aldosterone secretion. So in order for angiotensin 1 to be converted into angiotensin 2, it needs a hormone which is the angiotensin converting enzyme which is available in the lung. So this is how the respiratory system helps in the BP regulation. Of course, again, we have respiratory system is beneficial in our speech. We need our respiratory system for us to speak. and also to excrete some volatile substances. So this is more of the gases, volatile substances, and also to maintain body temperature, because when we breathe out, we also breathe out some water vapor. So again, these are the functions of the respiratory system. Okay, before we go any further, I think anatomy has already teach you about the structure of the respiratory system. So this is just a recap. So we can divide your respiratory system into two parts: the upper part, the upper respiratory system, and also the lower part. So the upper part also we call as conducting zone, and the lower part is the respiratory zone. So in the conducting zone, it is from the trachea up until the beginning of bronchioles. So why is it called conducting zone? Because at this area from the trachea until the beginning of bronchioles, the air is being transmitted or is being conducted. So there is no exchange of gases here. So it is only purely for the conduction of gases. So this is why it is called as conducting zone. Then from the bronchioles downward all the way to the alveoli, this is what we call as respiratory zone. Because why? This is where the area in which there will be exchange of gases. Oxygen going up to the capillary, and carbon dioxide from the capillary going into the alveolus. So this is the two structure of the respiratory system. Okay, just briefly the functions of the upper and also the lower respiratory system. So again, the upper, we have the cilia, the mucus, the phagocyte. So it is important in the defense mechanism. And also the upper respiratory system, the upper respiratory tract has water droplets on its surface. So what does it do? It is to warm and also to humidify the inhaled air into the lung, because the air that goes in is just air. So when it goes into our respiratory tract, it will be warm and it will be humidified by the water that is available in the respiratory tract. Okay, and then also for speech. Okay, again lower, it is for exchange of gases, as we have said before. Before we start to discuss more about mechanics of ventilation, so you need to understand first about the respiratory pressures. So in respiratory system, there are three important pressures that you must remember. Number one is the intra-alveolar pressure. Some books will name it as alveolar pressure or intrapulmonary pressure. So basically, it is the same: intra-alveolar, intrapulmonary, or alveolar pressure. So what it is actually pressure within the alveoli. So now remember, inside the lungs we have these alveoli. So inside the alveoli is what we call as intra-alveolar or alveolar pressure. So this is the pressure inside the alveoli. So the second pressure that you need to know is actually the intrapleural pressure. So what is the intrapleural pressure? So if you see the lung here, so you can see that, okay, the lung is actually is being held by the trachea here. So this is the hilum here. So you can see this is the pleura. So the outside is actually the parietal pleura, and the inside is the visceral pleura. So this is what we call the pleural cavity or the pleural space. So this space is actually empty or vacuum, but it has a bit of what we call that as lubricant for the pleura to be able to move without any friction. So this pleural cavity, the air inside the pleural cavity is what we call as intrapleural pressure. So the intrapleural pressure is always negative except in forced expiration. So why it is very important for the intrapleural pressure to be kept negative, because it actually helps to keep the alveoli open. So it is actually pulling the alveoli. So alveoli is inside. It's the pressure that pulls the alveoli out. So the alveoli won't be collapsed. So that is the intrapleural pressure. So in any instances in which the intrapleural pressure is not negative, meaning let's say there's ada macam stab wound. So if there's a stab wound, so if there's any what you call as pneumothorax, so meaning there is a breach between breach in the intrapleural cavity. So air from the atmosphere can goes into the intrapleural cavity. So when air from the atmosphere goes into the intrapleural cavity, so the pressure inside the intrapleural space is the same as the atmospheric pressure. So it is no more negative. So when it is negative, it is unable to pull the alveoli open. So it will compress the lung, so the lungs will collapse. So that is the importance why we need to keep the intrapleural pressure negative. So the third pressure that you need to understand or you need to know is actually the transpulmonary pressure. So transpulmonary pressure is basically the pressure difference between the alveolar and intrapleural pressure. So meaning alveolar pressure minus intrapleural pressure. Okay, so let's say the alveolar pressure is 760 and then the intrapleural pressure is 756. So when we calculate, so transpulmonary pressure would be 760 minus 756. So it will be 4 millimeter mercury. So if you see here, the transpulmonary pressure is the same amount or value with the intrapleural pressure, but in a different direction. So transpulmonary pressure is positive, it is always positive, and the intrapleural pressure is negative. So transpulmonary pressure is actually it is equal to the intrapleural pressure, but at the different direction. So this transpulmonary pressure is actually it is the equal and opposite of lungs elastic recoil. This slide shows the respiratory pressures too, but unlike the previous slide shows the respiratory pressures and the location in terms of the location where it is in the lungs. But here this slide is looking at the values of these pressures and we plot it into a graph. So again, here we have the alveolar pressure or intrapulmonary pressure. So it is, you can see the pressure differs. So from a bit positive to negative. So there's a pressure changes between positive and negative. So this is the pressure within the alveoli. So if you can see the intrapleural pressure, so intrapleural pressure, it is always kept negative. Okay, so it is always negative. You can see here at the beginning of inspiration, it is about minus 5, and then when inspiration takes place, it's becoming more negative, and then when expiration occurs, it is still negative but becoming less negative. So it is always need to be kept negative. Again, as we have discussed before, intrapleural pressure need to be negative to help to keep the alveoli open. Okay, and then the pressure difference between the alveolar and also the pleural pressure is the transpulmonary or transmural pressure. So the pressure difference or between these two pressures is the transpulmonary pressure. So the transpulmonary pressure is actually equal and opposite to the lungs elastic recoil. So next we will learn more about elastic recoil. Okay, So what is elastic recall? So basically elastic recall is the ability of a stretched object or organ to return to its resting position. So in respiratory system, we are focusing in two types of recall, which is the elastic recalls of the lungs and also the elastic recall of the chest wall. So I'll be discussing about the elastic recall of the chest wall first. So if let's say what does it mean by elastic recall of the chest wall? Let's say if we cut open our thoracic cavity, yeah. So if we cut open our thoracic cavity, so what will happen to the ribs? So the ribs would be jutting outwards, yeah. Dia akan terkeluar. So it will jut outwards. It will not move into place. Let's say we cut our sternum kan, kat tengah-tengah at the center. So the ribs would be jutting out. So that is the elastic recall of the lung. So it is prone to pull the thoracic cavity or thoracic cage outwards. So this is due to the elastic nature of the ribs itself, the muscles attached to the ribs, and also the tendons in the thoracic cage. So it tends to move out. Okay, so that is the elastic recoil of the chest wall. Then we also have the elastic recoil of the lungs. So it is in the opposite direction as the chest wall. So here the lungs are prone to shrink, to pull the lung inwards. Let's say if you take out the lung from a human, you put it on the table, the lung will shrink. It will shrink because it is due to two forces. So one is actually tissue forces and the other one is the alveolar surface tension. Okay, so let's go first into the tissue forces. So what is it? So we know that the lung parenchyma has elastin, has collagen. So all these are actually quite elastic, and when you cut open the lungs, it will pull the lung parenchyma inwards. So that is the tissue forces. So the other force that contributes to the elastic recoil of the lungs is the surface tension. So the alveolar surface tension. So if we can see, I draw here, this is the alveolar. So the alveolar surface tension is actually prone to collapse the alveoli. Okay, so the alveolar surface tension will pull the alveoli together and the alveoli will collapse. So imagine if all the alveoli in the lungs have increased the surface tension, so all the lungs in the alveoli will collapse and then it will pull the lung inwards. So that is will contribute to the elastic recoils of the lung. Okay, so normally the elastic recoils of the lungs and also the chest wall is in balance. So you can see that it is must be in balance so that you can create your intrapleural pressure or intrapleural space are maintained. Okay, so the next slides I will be talking more about the alveolar surface tension. Okay, remember I said that the surface tension of the alveolar is contributing to the elastic recoil of the lungs. Okay, so what is surface tension? Okay, so if you see a drop of water, so if you put a drop of water on the surface, which is clear and also smooth surface, let's say like a glass, you put a drop of water, so the water would stay as one nice drop like that. So why is it so? Because the what happened is the water molecules inside the water droplet actually pull each other. Okay, so inside they pull each other. So inside the water, as you can see here, the inner molecule is pulled in all direction, but at the surface, the molecule is pulled inwards. So if at the surface all the molecules are pulled inward, so you can see that like in the picture here, the water would form one nice drop because at the surface all the water molecules will bind to each other. Okay, so that is water surface tension. So if we put this surface tension in the alveolus, okay, so in the lungs or in the alveoli, there are water molecules. So there are water molecules in the surface of the alveolus like this. So a lot of water molecules. So nature of water molecules, they need to bind with each other. So let's say if the surface is full with water, so what will happen? All the water molecules are connected to each other, so they pull each other to form a tight area, just like the water droplets. So if this happen, meaning the surface tension is increased. Meaning if let's say these water molecules bind closely to each other, it will pull the alveoli to become smaller because these water molecules need to be near to each other. So they pull, it pulls here, this molecule pulls here, and in the end, what happened? The alveoli would be small. It will be smaller because the water inside the surface of the alveolus is pulling each other. So that what happens in the alveolus. So this is not the thing that we want. We don't want this to happen. So the slides after this will tell you what will happen if this occur. Okay, so remember the previous slide when there's water inside the surface of the alveoli, so it will pull the water molecules closer, and eventually it will pull the alveoli to become smaller. So when smaller alveoli, meaning the radius is decreases. Okay, so we don't want this to happen. We don't want the radius to decrease. Okay, why? Now I will introduce you to Laplace law. So you can just read here what the Laplace law said that, but actually the Laplace law said that pressure is directly proportionate to the tension, and pressure is not directly proportionate to the radius. Okay, so let us see here the Laplace law. So let's see here, if let's say we have two bubbles, so the bubble here is the alveoli. So here we have alveoli A and here is alveoli B. So according to the law, it says that pressure is not directly proportionate to the radius. So in smaller alveoli, so let's say this alveoli is smaller because there is pulling of the water molecules. Remember, we have the water molecules here. So the water molecules tend to stick with each other. So they pull the alveoli to the center. So the alveoli become smaller because the radius become smaller. So remember Laplace law said that low radius is high pressure because pressure is indirectly proportionate to the radius. So there is higher pressure in alveoli B. So if these alveoli are connected, what will happen? So you know that air will move from area of high pressure to area of lower pressure. So the pressure would move from alveoli B into alveoli A. So when air moves from alveoli B to alveoli A, it will decrease the radius. So again, when the radius is decreased, you will increase the pressure. So when the pressure increase, again the air from alveoli B will go to alveoli A. In the end, there's no more air in the alveoli B, and what will happen? The alveoli B will collapse and alveoli A will become bigger and bigger. Let's say if this happen throughout the lungs, meaning if let's say the surface tension of the alveoli is increased, meaning there is a lot of water vapor. So all this water vapor will pull the alveoli, and alveoli become smaller, and eventually the alveoli will collapse. So this is one alveoli. So imagine in the whole lung what will happen if all the alveoli collapse. Then it will be very, very, very difficult for us to breathe, because when we want to open up a collapsed alveoli, it will take a lot of energy, and it's very difficult to open up a collapsed alveoli. So we don't want this to happen. So how does the body deal with this alveolar surface tension? So with the secretion of surfactant. Okay, so I'll be discussing about surfactant in the next slide. Okay, so how does the body overcome this surface tension? Is by surfactant. So what is surfactant? Surfactant is a substance secreted by type 2 alveolar cells. So it has some hydrophobic and also hydrophilic region. So what does surfactant do? If you can see the diagram here, so the diagram on top is what happens if there's no surfactant, meaning if there's no surfactant, the pulling pressure or the surface tension in the alveoli becoming higher and higher and higher. So it will, again, based on the Laplace law, so when low radius, there will be higher pressure. So air will move from area of higher pressure to area of lower pressure. So eventually the alveoli will collapse. But with surfactant, what happens is surfactant is secreted in the lungs itself, and it will insert itself in between the water molecules. So if you can see in the picture here, so it is inserted in between the water molecules. So when it is, let's say here, water molecule, water molecule, water molecule. So when we put surfactant here, actually we are breaking the bond between the water molecule. So when we break the bond from the water molecule cannot pull each other. So it is disrupted. The attractive forces is disrupted. So when it is disrupted, so we are actually reducing the surface tension. So when we reduce the surface tension, the diameter of the alveoli will not becoming small. Okay. So again here with surfactant, what happens? The surface tension is reduced. So when we reduce surface tension, again diameter will not be as small. Okay. So when we come the so the formula here, remember 2 times the surface tension. So if we reduce the surface tension, the pressure would now become the same with a larger alveoli. So with surfactant, actually we are making sure that every alveoli has about the same pressure. So when every alveoli has the same pressure, there's no issue of movement of pressure or movement of air from higher into lower concentration. So if there's no movement of air between the alveoli, so the alveoli all are open. So alveoli all are open, and there is a less chance of the alveoli to collapse. So it is easier for us to breathe. So that is how the body overcome the alveolar surface tension. Okay, as we have discussed before, surfactant is secreted by type 2 alveolar cells, and is secreted during late gestation period. So if a baby is born prematurely, meaning born earlier than their gestational age, usually they have low surfactant level because they don't have the time to secrete surfactant. So it will lead to infant respiratory distress syndrome. Okay, so here what happens is when they are born, the alveoli will easily collapse because the surface tension is increased. Okay, so this is in babies. In adults also can have a decrease in surfactant. So those who have long-term oxygen inhalation therapy, or those who have smoked cigarette for a long time, they also are prone to get a decrease in their surfactant level. Okay, So thyroid hormone will increase the secretion of surfactant, and glucocorticoids will accelerate the maturation of surfactant. So as we can see, surfactant is very important for our normal breathing. So next, I will be discussing about the mechanics of normal breathing. So before we discuss about mechanics, you need to really understand about the concept of surface tension, concept of recoil, and the pressure. So after you have understand all those concepts, then it is easier for you to understand about the normal mechanics of breathing. Okay, so before we discuss the mechanics of respiration, so I would like you to understand that there are two types of breathing, which is quiet breathing and forced breathing. Okay, so again, quiet breathing we have consists of inspiration, expiration, same as the forced breathing, we have inspiration and also expiration. So what is quiet breathing? So quiet breathing is the breathing that you have on a day-to-day basis, when you are resting, after eating, when you're sitting down watching TV. So that is quiet or tidal breathing. And we have here what we call as forced breathing. So what is forced breathing? So forced breathing is the type of breathing that you have when you are exerting yourself. For example, when you are exercising, when you are running around. So this is what we call as forced breathing. So meaning the breathing is higher than the normal quiet breathing. Okay, so before we proceed into the mechanics of ventilation, so I would like to introduce you to another law. So here is Boyle's law. Remember, just now we have discussed about Laplace law. So now we are discussing about Boyle's law. So what does Boyle's law say? Boyle's law said that pressure is indirectly proportionate to the volume. So this is in a enclosed space, yeah? Enclosed space like in your lungs lah. Okay, so meaning if pressure is high, meaning the volume is lower. So it is indirectly proportionate. So Boyle's law is very important, so you need to remember this so it is easier for you to understand about mechanics of ventilation. Okay, so I will be discussing about quiet breathing first. So first I'll be discussing about quiet inspiration first. Okay, so inspiration, what happens during inspiration is actually we inspire air from the atmosphere. So when we breathe, we want the air to come in from outside, meaning from atmosphere into our lungs. So that is inspiration. Okay, so we know that air moves from higher pressure area into lower pressure area. So that is the movement of air. So in order for us to inspire, we know that we need to reduce the pressure inside our lung cavity. So when the pressure inside our lung cavity is lesser than the atmospheric pressure, then the atmospheric pressure can go into our lungs. So that is our aim in inspiration. We want to decrease the pressure inside our lung cavity. Okay, so meaning what we want to do is we want to decrease our intrapulmonary pressure. So how are we going to decrease our intrapulmonary pressure? By changing our intrapleural pressure. Okay, so if we change our intrapleural pressure, which we will discuss in more detail after this, we will be able to decrease the intrapulmonary pressure. So how are we going to able to change the intrapleural pressure? Is actually by changing the size of the thoracic cavity. So if we change the size of the thoracic cavity, we will be able to achieve a change in the intrapleural pressure, and thus will decrease the intrapulmonary pressure. So how are we going to change the size of our thoracic cavity? Is by the actions of respiratory muscles. Okay, so we can see the flow here. So we need to decrease the pressure inside the lungs. So to decrease that, we need to change the intrapleural pressure. So in order to change the intrapleural pressure, we need to change the size of the thoracic cavity. How are we going to do this? By the action of the respiratory muscles. So these are the concept that you need to understand. So next I will be I'll be telling in detail about the mechanics. Okay, so remember that our aim for inspiration is for the pressure inside the thoracic cavity is lower than the atmospheric pressure. So remember how we're going to do it. We are going to contract the muscles of inspiration. So again, inspiration is an active process. Okay, so what happened first? We have a diaphragm and we have the external intercostal muscles. So these two are muscles of quiet inspiration. Okay, so when we contract the diaphragm, okay, so the diaphragm is here. So the diaphragm is actually a dome-shaped muscle. So if we contract the diaphragm, what happens? The diaphragm will flatten. So from like this, when we contract, it will become like this. So it will be flattened. Okay. So when it is flattened, what happens is actually we are increasing the vertical diameter. So from here it goes down. So the whole of the vertical diameter increases. Okay. So when diaphragm contract, the vertical diameter increases. Okay. So why we need to increase the diameter? So because when we increase the diameter, we are actually increasing the volume of the thoracic cavity. Remember Boyle's law? Decreased volume means pressure is lesser. Remember our aim of inspiration? We need to decrease the pressure inside the lung so that air from the atmosphere can goes in. Okay? So when diaphragm contracts, it flattens and increase the vertical diameter. So the other muscle of quiet inspiration is the external intercostal muscles. So what happens when external intercostal muscles contract? It will pull the rib upwards and outwards. Yeah, meaning it will increase the AP and anteroposterior and also the transverse diameter of the lungs. So when it is increases the diameter, okay, now when we have increased the vertical, the anteroposterior and also the transverse diameter, so we have already increased the volume of the thoracic cavity. Okay, so once the thoracic cavity has increases, the pleura is also stretched. Remember, the pleura is we have the parietal and also the visceral pleura. So imagine here is the lung. So we have the parietal and also the visceral pleura. So when the parietal pleura is the one which is attached to the thoracic cavity. So once the thoracic cavity has increases in size, it will pull the parietal pleura away. So meaning that, but then the visceral pleura still remains the same. So we are only moving the parietal pleura because it is attached to the thoracic cavity. So what happens when we pull the parietal pleura? We are actually increasing the intrapleural space. So imagine initially it is like this, but when we put the parietal pleura, the intrapleural space is going to increase. So when we increase the intrapleural space, again we refer to Boyle's law. When the volume increases, the pressure will become lesser. So in the intrapleural pressure case, it is becoming more negative. So when it becoming more negative, so remember the intrapleural pressure need to be negative so that it will pull the alveoli open. So when it is becoming more and more negative, so it will pull the alveoli or expand the alveoli more than usual. So when we pull the alveoli, again it will increase the volume inside the alveoli. Thus the pressure inside the alveoli will be less. So again, intra-alveolar or intrapulmonary pressure decreases. So when it decreases below the atmospheric pressure, then the air will move from the atmosphere into the lungs. So when we're talking about quiet breathing, the usual amount that is inspired is about 500 mils of air. Okay, so let us look here at the graph here. So this is also the same. This is what happened during quiet inspiration. So if you can see, the pressure inside the intrapulmonary is decreasing during inspiration. So 0 is the atmospheric pressure. So during tidal inspiration or quiet inspiration, this is the amount of the or the decrease in terms of intrapulmonary pressure. So you can see that this quiet inspiration will draw about 500 ml of air per cycle. Okay. Okay, so now we're going to talk about quiet expiration. So after inspiration, there must be expiration. So compared to inspiration, quiet expiration is a passive process. So basically, it is the opposite of what happened during inspiration. So for quiet expiration, these are the things which actually we need to decrease the thoracic cavity. So the aim of expiration is we want the air inside the intrapulmonary, meaning the pressure inside the alveolar is higher than the atmospheric pressure. So if it's higher than the atmospheric pressure, then the air inside the lungs will go into the atmosphere or will go outside the lung. Okay, so how do we achieve this? Meaning, how do we achieve the increased pressure inside the lungs? Okay, so again we need to decrease the thoracic cavity, because when volume, again Boyle's law, when volume decreases, pressure will increase. So how do we achieve decrease in the thoracic cavity? So it is due to, first one is the relaxation of the diaphragm and external intercostal muscles, because during inspiration they are contracting and then here they need to relax. And then we also have the elastic recoil of the lungs and the elastic recoil of thoracic cage. So all these will make the thoracic cavity volume decreases. And then when we decrease the thoracic cavity volume, what happened? The pleural cavity volume will also decrease. Remember? So we have the, here is the visceral pleura and here is the parietal pleura. So when everything is moving back into its original position, we are actually decreasing the pleural cavity volume. Thus, we are increasing the intrapleural pressure, meaning it is becoming less negative. And then, once the intrapleural pressure is becoming less negative, it will compress the alveoli. So when the alveoli is compressed, again, volume is decreased and it will increase the intrapulmonary pressure. So once the intrapulmonary pressure is higher than the atmospheric pressure, air will move out from the lung. Okay, and then the expiration process is complete. Okay, now we are going to move into forced breathing. So here I will discuss first on forced inspiration. Again, it is an active process. So remember when I told you when do we have forced breathing or forced inspiration? So So it is during exertion, when we are exercising. So here we need more and more oxygen. So we need to breathe in more air. So for forced inspiration, the process is the same as quiet inspiration. But the difference here is because we need to have more air to flows into the lung. So meaning we need the pressure inside the thoracic cavity, or we need the intrapulmonary pressure to be lower than the pressure during quiet inspiration. So when the pressure is much lower, then more air will be able to come in from the atmosphere. So how do we achieve this lower pressure in the intrapulmonary area or inside the lungs? So by increasing more and more of the thoracic cavity size. So when we increase the thoracic cavity size, we are going to decrease the intrapulmonary pressure. So how we are going to increase the thoracic cavity size more than during quiet inspiration? We need to have additional contraction of muscles. So here, for forced inspiration, we do have the same contraction of the diaphragm and also the external intercostal muscle, but we also do have additional contraction from accessory muscles. So these are the accessory muscles of inspiration. We have the sternocleidomastoid, the scalene, and also the serratus anterior. So this will lift the sternum up, lift the ribs, and lift all the ribs. So this will increase the thoracic cavity much more than during quiet inspiration. Okay, so now we move on to forced expiration. So if we compare forced expiration and quiet expiration, so forced expiration is an active process. So here again we need to make sure that the intrapulmonary pressure is high so that it can move the air from inside the lung to the environment. Okay, so how do we achieve this? By decreasing the volume of the thoracic cavity. So we will decrease the volume much more than during quiet expiration. So how do we do this? Is again by the contraction of accessory muscle of expiration. So here we have internal intercostal muscle. So this muscle will pull the ribs downward, and this will lead to decrease in the transverse and also the anteroposterior diameter. So in terms of vertical diameter, how are we going to decrease it? So by pushing the diaphragm upwards. So remember, diaphragm is a dome-shaped organ. So it is here during inspiration. So when we want to expire, so it need to be dome-shaped again. So we need to push the diaphragm upwards. So what is there to push the diaphragm upwards is actually the muscles of the abdomen. So contraction of the abdominal muscles such as the rectus abdominis, transverse oblique, internal and the external oblique will increase the pressure in the abdomen that will push the diaphragm upwards. Okay, so this will decrease the thoracic cavity, thus increasing the intrapulmonary pressure, and air will be forced out from the lungs. Okay, so now we'll discuss about the effects of gravity on the lungs. Okay, so when we stand up, the gravity pulls down the lung. So the lung has its own weight and is only connected in the hilar region. So the rest, it is left hanging inside the pleural cavity. So it is only attached in the hilar area. So when we stand up, the weight will pull it down. Okay, so now we are looking at what happens at the apex and what happens at the base. So base is here, down here, and up here is the apex. Okay, so when we stand up, okay, so let us imagine here is the parietal pleura, which is connected to the thoracic cage, and here is the visceral pleura. So when we stand up, the lung goes down a bit. So meaning that the visceral pleura will goes down a bit, and thus we are actually increasing the volume of the intrapleural space. So when we increase the volume of the intrapleural space, the intrapleural pressure will decrease. So here it becomes more negative. Okay. So what happens when it becomes more negative? The transmural pressure is higher in the apex. Remember, transmural pressure meaning alveolar pressure minus the intrapleural space. Intrapleural pressure. So it is becoming higher than the base. Okay. So when transmural pressure is increased, it means that there's not much opening and narrowing of the alveoli during respiration. So it is already open up. Okay. So when there's not much opening and narrowing during respiration, this is a condition that we call as decreased compliance. So I will discuss compliance in my next slide. So when there's decrease in compliance, meaning the ventilation is decreased. Okay. So in the apex, what happened is the ventilation is lower than in the base. So because when there's decreased compliance, meaning the alveoli distensibility is decreases. So when there's decreased distensibility, meaning there's already air inside the alveoli. So when there's already air inside the alveoli, the new air that comes in will not go to the alveoli in the apex, because alveoli in the apex has already have air inside the alveoli. Okay, so now we look at the base. So what happened is the weight will go down. So it will go down to the base. Thus, the intrapleural volume is lesser in the base. Yeah? It's opposite of what happened in the apex, meaning that the intrapleural pressure here is increases, meaning becoming less negative. So if we compare the transmural pressure, the base has a lower transmural pressure. So what does it mean? It means that the alveoli here are easily opened and closed during respiration, meaning there's more compliance, thus it will lead to better ventilation. Okay, so in the base, again, when the alveoli is more compliant, meaning it is highly distensible. So it is more distensible than the alveoli in the apex. So if it's easily distensible, so when air comes in, it will go to the base because it is easy for the base to be distended, and the air will go to the base. Okay, so if you don't really, if you're not very sure about the effect of gravity on the lungs, this topic will be discussed further in topic number 3. Okay, but this is what is happening in the apex and in the base. Okay, so here is compliance. So what is compliance? Compliance is basically the ability of the lungs to stretch and to expand. So when air goes in to the alveoli, so how easy the alveoli is to expand, to stretch and expand, that is what we call as compliance. Okay, so when compliance is high, meaning that the lungs are easily distended. But if the compliance is low, meaning that the lungs are stiff and it is difficult to expand and stretch, or what we call it as less elastic. Okay, so what are the factors that determine the compliance of the lung? So it is determined by the lung factor and also by the thoracic cage. So again, in the lungs, remember you have the elastic recoil. So all these will actually play a role also in the compliance. So again, lung tissue is distensible because of the presence of elastin and collagen, and also because of the surface tension of the alveoli. Okay, so for thoracic cage, it is due to the distensibility of the thoracic cage itself, the sternum, the ribs, and then the muscles in between the ribs. Okay, so if you can see here, this graph is showing lung volume and the transpulmonary pressure. So in the center is the normal compliance. So here on the left side is the graph, those with high compliance, meaning that with even with low transpulmonary pressure, low pressure inside the lung, the volume of the lung increases very much, meaning it is highly distensible. For low compliance here, meaning that even with increase in pressure, the volume will not increase that much, meaning that it is very difficult for the lung to expand. So usually this is the case in pulmonary fibrosis, in which the alveoli are fibrous and it's very difficult for it to expand. Okay. Okay, so this will be my last slide. So only a bit on work of breathing. So what is work of breathing? It's basically the work that the lung has to overcome. So during quiet inspiration, there are three pressure or three work that the lung has to overcome. Number one is the compliance work or elastic work. So this is the work of breathing against the elastic forces of the lungs and chest area. And then we do have the tissue resistant work. So this is the work that the lung has to do against the viscosity of the lungs and the wall structure. So this is basically the lung parenchyma itself. And then the third one is the airway resistant work. So this is the work that the lungs has to overcome against the resistance of the airway. Okay, so again, work of breathing is increased during exercise, and then during any disease that will obstruct the lung, such as bronchial asthma, because the lung we need to breathe more, we need to work more for us to be able to breathe in this condition. So the work of breathing is increased. Okay, so that's the end of the first lecture in respiratory module. So if you do have any query, please don't hesitate to call me, to text me, or to drop me an email. Okay, so thank you everyone.